Yeah, there are a lot of twos in this broadcast. This is week 2, spreadsheet modeling 2, part 2, part 1 of part 2 of 2. I hope you had a nice rest from the part 1 presentation. And I want to go back and say this is the fundamental equation of finance right here. It has to do with time, risk, return, generation of cash flow, generation of value. It can be deterministic. It can have probability distributions associated with it, but it is fundamental. It's also fundamental in supply and demand, but we're using it in our model to accumulate a present value, which is way down here. Start looking at this multi-period model. You see several things. First of all, a lot of documentation on the right. You see this big box down here, which has a value equal to this small box here at C27. That is C27. It has a bigger formula in it. That's because it has all the algebra in it, implemented in a programming language that's been used for quite some time called Visual Basic for applications. It's a way to automate routine tasks, including routine calculations inside of Excel. We'll look at that in a moment. But just look at the structure of this model. The format, we have different descriptions of each and every row. Okay, but across the top, we have 3 periods. There's a lot of different ways of doing this. You could flip this around and have the time periods going down as rows, and all of these decision variable model parameters and everything else going across in columns. It's up to you. It's whatever works. And really whatever works for the client or your analysis team. And everything is a formula. Even this start out with 0 and you advance it by 1. 2 is equal to 1, whatever's in 1 plus 1. 3 is whatever's in 2 plus 1. Everything's a formula, keeping away from the idea of hard coding. Right now, 0 is hard coded. We could make 0 2020. And this would therefore be 2021, 2022, 2023. We could do that. We should do that. When we do that, we should put it in a setting. The price that this model calculates at is $8 currently, producing a net present value of 1,951,000 and change. These accounting conventions are not necessary here. They really aren't. We're not going to worry in a model like this with that. Up here, they do matter. And you can remember, here is the complicated situation of the cost parameters. D12, where's D12? That's the 45,000 number, is divided by 52,000. That's 52 times 1,000. And that's because we were measuring volumes and costs per 1,000 pies weekly. This is an annual model. This one over here. This is like 13,000 or whatever it is times 52 weeks. And I should probably be documenting that over here. Well, you should too. And the model runs pretty easily when we think that consumer demand in thousands of pies. Okay, this is weekly here. So this must be a number that's, yes, times 52. Times 52 times 52. And according to that, a price drives this schedule. Price, therefore, drives through 468,000 pies in a year. And that's not very many, by the way. It doesn't feed a lot of people. It's a small number in the world of today, at a cost of $15.89 a pie per year, per pie. 14, 12. The costs are going down. The costs are going down because it's partly dependent upon this quadratic shape of the cost curve, which we see over here. You see the squared. There's a squared here. There it is. There's a squared. Here's the linear term, the so-called linear term. It's really a straight line term. The whole thing is linear, but we won't get into that. And we have total revenue, which is price times demand. We have total material cost, which is fruit filling and dough cost times volume. Volume produced is volume sold. Now, in a real model, this is real enough, but in a real model, we would probably have some carrying of inventory from time to time, incurring another cost. And in the case of these pies, they're probably going to be frozen pies. That carrying cost could be rather large, between the insurance, the floor space and the lease, the equipment, the energy powering food freezers, walk-in or otherwise, the handling that is going to be different, processing, handling, distributing, all of that increases cost. Perhaps. Yeah, it does. And we calculate this material costs and get a so-called profit. It's what the client wants is profit. This to me is not profit. It's kind of a profit, but an accountant would say, wait a second, be very careful about your nomenclature, and I would agree. And we're generating positive profits here, but a negative net present value. So the profit picture may look great, but against the $2.5 million investment, it's not very good at all. And if Simone Tortsier wants to sell this firm, or yes, have it acquired by a special purpose acquisition corporation, a SPAC, for example, a big question for her. She want to lose all of this money. They're not. How much would they pay for this is a real big question. And how much they would pay for this would come out here, let's say in year 3, as a separate line item. This is a line, and it would be a separate line item. It would be an additional, for example, multiple of first-year sales, or a multiple of third-year sales, a multiple of average sales over the 3 years. Well, we know what the sales numbers are projected to be. These, take an average, multiply it times 3, and you get a new line item. And I bet this goes away. Just bet. 3 times 77,000. That's a pretty big number. 200,000, not enough. Won't be enough. It's interesting that that's such a large number. That's a good number. These numbers look like normal. Is that correct? Oh, we need to go back and check that because it should be more in line with these numbers, I would have thought. Of course, that fixed cost is pretty big. Oops, that's going up. That's going up. Might be, maybe this is the culprit. So that's why we look at these models. Now, the other thing we do is we do sensitivity like we did last time. Here's the profit sensitivity, and we see that profits, as in the above model, are positive. Fine, good. This is the optimal prop, and notice we're using an index match. Yes, we are. Index and match. Find in B6 through B14 a price that is at the same row as the maximum profit. Maximum profit is at a particular row. What row is that? That'd be 1, 2, 3, 4th row again. There we go. 4th row here. $7.63. Then we can build a graph of this, a plot. Again, we have the setup, same as before, with a X, Y, AB line drawn from A to B, from A to B. But notice it's an interesting break even here. There's two of them. Now, this is a quadratic equation. You can see that parabolic shape from high school. It's there. Maybe even high school physics, which always says, and is technically wrong because it's an ellipse, but throw a ball up in the air and it's a parabola. Kind of interesting. So a little bit under $7 and almost $9 is the break even, somewhere in between. It's caused by the interaction between price and demand and supply. All of that creates that shape. And then we can do the same with, and again, why these are negative, truly not profitable over time, given the money that has been put into equity and booked. It's not positive net present value. Should expand this column so that it includes this item right here. Any other critiques? Yeah, maximum profit. This is the least loss, and it's $8. The optimal price at $8. And of course, you plot this. I did not put in the setup, but it's a similar setup. And here's $8. It's the highest in a trajectory of a pretty bad trajectory. Now, there's no break even here. If you remember high school, this is where complex numbers, imaginary numbers, come in play, because this doesn't solve for anything on this real number line. Okay, leave that alone for a moment. And then what we also want to do is brace ourselves in Scrapin is a two-way sensitivity analysis. And let's go to the Winston chapter 17 to look at that. And also in chapter 93. Plus there's a Microsoft help. Looks like it's being deprecated and upgraded on this same item. I mean, this is a good thing to do. It's not hard to produce. Follow the directions exactly. And when we do follow the directions exactly, we see something that looks very similar. Now, that's a lot of that stuff going on. All right. Actually, I don't know why. I think this is the result. That's an interesting display. This is called a markup, by the way, markup language. And it did not render in this particular version of life. An ASCII doc. Yeah, we could copy it out. That's true. We could probably render this, but we're not going to. It's already been rendered. In the rendering, we go back to this. There we go. Is here. So we go through. This is kind of important. So you set up a grid across the top. In this case, is for, I didn't even label it. It's horrible. Filling cost per unit. And from a low of 350 to a high of 450, thinking it's going to be somewhere in the middle. That's where it's going to land. But we're trying to sensitize ourselves to this. And we're not saying one is more important than the other. We're assigning a probability distribution called the uniform distribution to this, which is also the beta 1-1 distribution. But it is here and it is there. Got to think about what our assumptions mean when we're projecting into the future. We only can project in the future with probability, with plausibility, with credibility. I don't like to use the word confidence because I have no confidence in that. What I do understand is logic that shows data, assumptions, and so on, and model are all consistent with one another. That's really what's going on under the hood here. Oh, I just pointed at my head. Here. And this worksheet produces a two-way. This is price, and I have two ways of making the grid, filling cost and the price grid. In these rows are the price. In these columns are the grid of other things. And over here, the reference, this reference at 26, and I think we need to document where that reference comes from. That reference is actually to a spreadsheet, a separate worksheet just for net present value, just for this graph. When we do that and go to data, the data tab, and what if, and we go to data table what if, and then we go to data table itself there, we get this dialog, which asks us to input what this is. Now, what it's going to do is going to take this and dump it into the place where that minus 2632 is calculated. It'll first take this combination, 7.5 and 3.5, that combination, that scenario, dump it into the calculator, produce this cell, and it will keep doing that all the way through and all the way down. It's a nested for loop, basically. So you press OK, and you get this result. Great table. Okay, you can see it's a table. That's this thing here, and it has the two references, the row and the column, the row and the column in the table array function. Special function for this. But it is also referring to this. This whole thing is a table to Excel in an array. Oh gosh, optimal profit, optimal price, doesn't make any sense. These need to be changed, and they will be changed. Okay, so that's something to be done in the future. That took over 5 seconds to run. That's too slow for a normal production model. People don't like watching the little wheel go around, the little blue wheel. There's another way to do this, and it's also a check on the calculational integrity of our model, is to create this. And this is the algebra in this for loop, which calculates and accumulates present value calculations. So it's very finance-like. And back in the bad old days before this, right before the spreadsheet, we had a program called IFS, interactive, it really wasn't that interactive financial statement generator. And that's the sort of thing we would have to do, is enter equations and make sure they're all consistent with one another. Now, this is also familiar to folks. You could line this up in matrix algebra and create simultaneous. This is actually a simultaneous equation model, but it's a block simultaneous equation. One block, there we go. One block feeds into another. Okay, so it's a fairly straightforward one. There's very little interactivity there, but there is a financial statement generator, and the normal one that is used has a plug variable in it that has to be solved for. And it's usually around working capital. That's the one we usually choose. And that's the one that requires iterations. And actually, Excel can support that kind of a calculation. But this one's pretty straightforward. We're creating a new function as a public function, which means it's available to any worksheet in this, and even outside. Another worksheet can access this. Another workbook outside can access this. Kind of dangerous. And it's a bespoke, custom built, bespoke net present value calculation, where we have an initial, this would be minus 2.5 million. We have 10% here. We have an initial price. We have price growth. We have intercepts for and slope for the demand. All of that needs to be written out here. Slope and quadratic shape parameters for cost. Dou, the initial $3.50 from above. Dou cost per unit. Dou cost per unit growth. Filling cost per unit. Filling cost per unit growth. Fixed cost per unit, not per unit, but per year, would have to be calculated from this. I was using a weekly number here, and thus the 52. I mean, all of these dimensions have to be, and growth in it, and time. Time is 3 years. It's a 3-period model. At the end of date 3, boy, we got it. And this, we set PV, oh yeah, you got to declare all the variables. That's housekeeping. And their dimensions, and you can redimension them. But we start a present value tally at 0 and then start to accumulate it. As we go through time, we accumulate present value as we go through this over and over and over again. And again, in the battle days, what we used to do is we actually used to take numbers and calculate these by hand, loop those calculations. It's a lot of work, Next die just basically says move the counter ahead until the end of time. The end of time here is 3. It's only going to go through a couple of times. And the result is the name of the function, gives you a single result. We can also make functions that make arrays, and we've seen those. Linest, for example, is one of those. Transpose is another useful one. And table itself is an array function. So having done that, oh, I got to put this in here. Okay, I'll recalculate this. This is a little logical thinking problem. The thinking involved in making that is different than the thinking involved, that function is different than the thinking involved in Excel spreadsheets. Thinking involved in Excel spreadsheets looks an awful lot more like an Intel processor assigning memory. And I've got this reference of an example for an 86 register. You know, where's memory? It's got memory names and so on. There's programming that gets you in and out of this memory and says, put stuff here for a while, here, and here, and then over here, add them up. And there's other routines, popping and pushing and shoving, literally shoving things around in memory. That's how the computer actually operates. And this is actually interesting if you don't know about this. But here we're declaring a byte, declaring unfinished bytes, declaring more bytes with a label in order to produce something like calculate a sum. All right, I think there might be one here with instructions. And there should be one push, what push does, what pop. This is exactly what Excel does in cells, and the addresses of Excel. These are very similar. So anyways, not to get excited about that, but to realize that that's how it works. All right, so that's a two-way sensitivity analysis. And we have the table. Very slow. This is very fast. Very fast. I can't blink and it's gone. And what I do is I take a little aside and give you another beast of a formula, but it's a formula. You can put it together and it works. This is the standard, not the standardized. It's really, yeah, in a sense it's standardized. Normal distribution function, mean standard deviation. Whenever you see a pi in something, it means it comes out of a circular function. It's actually related to Ptolemy, the Egyptian astronomer from Alexandria, not Virginia, Alexandria, Egypt. The Alexandrian Library, Alexander the Great, who was around for 13 years and changed things pretty radically. He wanted to chart movements of objects in this in the sky, stars, and for navigation mainly, and planets for seasonal movements. Okay, seasonal movements. You see Orion in the sky, it's probably winter in the north. You see it in the southern hemisphere, it's probably summer. It's their winter, our summer. Um, where is it and when is it going to happen? It was good to figure out floods and famines and other things like that, weather, partly. And he was able to track planets incredibly accurately using an algorithm called an epicycle algorithm. Look it up. But basically, it's this Gaussian function. Fascinating. If we have, for example, some data like price equals $9, how plausible, and this is a research question, how plausible is it to observe a price that is $9 per pi when the mean and standard deviation are various values? We need to sensitize ourselves. And now this follows a Gaussian distribution. Kind of interesting. Same grid, or it should be the same grid, like from 6 until 10, and from 3.5 to 4.5. Well, whatever. And now these are probabilities that you'll see a particular price and filling cost combination 9% of the time. Yeah, kind of interesting. By the way, these will not add up to 1, but they are still probabilities. We would take this number and divide it by the sum of all these to get the actual probability. That's how life works. Okay. And you can see that beast of a function is down here, but you can also use simply norm.dist to get there. Okay, and along with that, okay, yes, we could have used that, and there's quite a bit of that in. Let's see if I have it down here. I didn't put it down, but I need to fix that because I want to show you where that comes from, and where it is inside of Wayne Winston. I will update this for you. But there we go. And now we put a little color into it. But there's a big controversy over this too. I just like to see it there because it's a little bit, makes me ask, why is this red and why is this green? Well, that's because that's the most red and that's the most green. So I guess red and green mean we have to put a legend in probably. Red is worse and green in this case is less worse. Heat map. You can see the way it flows. Okay, it gets bad in here and then it gets really bad up here. Low price, high cost. Makes sense. And that is always one of the things we got to see with everything we do. Does it make sense? But also interesting, it gives me exactly the same numbers as the one directly off the spreadsheet using data table. I've got some sort of validation meaning confirmation, meaning strength, health, hygiene, something that our model is working as at least as we programmed it. Okay. And then we go beyond. Oh, by the way, you got to look at this. Osama Saleh writes a great article. He works for FAIR, which is a risk modeling and software company. Pretty good model, very interesting model. And when I say interesting, it means I think I want to get into it more. And he references the risk management standard called ISO 31000, and basically says, according to that, heat maps are bad for your health, and in some ways they are. But again, I'm using it for not to bend something, but to show what's worse and what's bad immediately. And here it is, the final thing, with all of the glory of every single thing. Now, there's another thing here called goal seek, but don't do that with this model. We can do it with Make-a-Pi, and there's a lot of goal-seeking information in Wayne Winston, but I tend not to use it too much. It's a little bit difficult to use, and if you have a highly nonlinear response function, you couldn't calculate this up here, for example. It'd be impossible to calculate. Why? Because there is no break even. Here, I'm looking for a break even. It's going to find one, but not the other. Which one is it finding? I don't know. I need to see this. I need to have other ways of imagining a solution. Okay. Every worksheet has a different component of all of this job that has been done, including storing separately NPV pi. Okay. Got a lot to do here, Simone Torcier. And of course, if she likes it, we're going to keep it. If she doesn't like it, what else would you like to do, Simone? How else would you like to relate things? Would you like to be able to choose a different setting up here and a different setting down here? You want to look at one cost versus another? That would be good. Price versus a different cost? That would be great. We can create a little list box of what other things to put on top, what other things to put along the side, automatically filling in what grid we're talking about. And this should be labeled net present value here somewhere. We should also be able to do exactly the same thing with weekly profit. So we could have another list box over here for which one do we want to see? Weekly profit, boom, or net present value, boom. Okay, that would make this even more interesting. And if not a list box, well, we could use list boxes. We could have a list of things in cells here and have them, when you press on the cell, go to a very little bit of VBA, uses something called intersect, for this sheet alone, a private function, private subroutine actually, and it automatically brings everything in. So you don't need a list box. Oh, okay, possibilities abound for interaction. No forms in this one. So I will figure out this for next loop. And this is the problem we're going to have with net present value. That's another thing to begin to think about. Years ago, Microsoft, early 90s, called present value a levelized payment. And then somebody says, well, we need to calculate present values for uneven payments. That's our situation, uneven payments. A levelized payment is called an annuity. And not a kind of a variable annuity, you can work into that. And that's an interesting thing to study from a spreadsheet point of view as well. And using a spreadsheet point of view as well. But unfortunately, they assign the annuity to the PV function. And uneven payments to the NPV function, the very first of those payouts is date 1, not date 0. And thus we have a problem. We basically, net present value is not net present value. It is present value without including the current date at which we might be shelling out money or getting money back in, proceeds, let's say. So just be careful. It gets confusing, and I've seen a lot of fatal errors made just with this one formula. That's why I like to tend to program my own discounts and growths and everything else, and not rely on somebody else's view of how that should be modeled. Because there's a modeling point of view here, and that's an extremely important part of any modeling decision. The decision that we're modeling, and then we're modeling a decision, but we have a model decision too. What model are we going to use? So I leave you with all of that. And user form controls here. Yes, okay. We have all of that. And I hope you enjoy this week. There will be a separate call out for a walkthrough of the case that will be due in a week, following Sunday, prior to week 3, in which case we will walk through that. Now that case, by the way, is going to be very similar to this. Going to use the tools inside of this with a couple of quirks, and it'll be as much diagnostic for us to see where are the gaps, where are the tough parts, what are the things we need to get back at. At the very least, documentation. And this is not complete. I got to complete it myself. Okay. I will update some little quirks in this and see you on the other side of a discussion. Also, remember there's a live session. I've scheduled another live session for 4:30 to 5:30 Eastern Daylight Time. Uniform time code -4 hours, UTC -4, on the Zoom channel. Okay. And hope you were able to view the live session from this past Friday. Anyways, I'll leave you with all of that. And of course, I thank you very much for your very kind attention. And holler if you need anything. Take care.